Hello everyone, welcome to Science Breaks. My name's Tom Davison. I'm a planetary scientist at Imperial College London, and I'll be chairing the event this afternoon. Today we're going to be hearing from Professor Gareth Collins, who's also a planetary scientist at Imperial College London. Professor Collins earned his BSc in geophysics with mathematics from the University of Liverpool in 1998, and his PhD in geology from Imperial College London in 2002, in which he used numerical modelling to study large impact crater collapse, which, as you'll see in the talk today, is still an exciting area of active research. After his PhD, Gareth moved across the pond to work as a postdoctoral research associate at the Lunar and Planetary Laboratory in the University of Arizona, before, in 2004, returning to Imperial College London, first as a Natural Environment Research Council research fellow and then an advanced research fellow, before being appointed as permanent staff in 2011 and a professor in 2018. Professor Collins' research explores the many consequences of impacts, not just on Earth, but across the solar system. He develops computer simulations to help understand this exciting, violent natural phenomenon. Professor Collins was involved in the IODP drilling expedition that drilled the Chicxulub impact crater in 2016, and is a participating scientist for NASA's InSight mission, which landed a seismometer on Mars in 2018. He's also an investigation team member of NASA's DART mission and on the impact modelling working group for the European Space Agency's HERA mission, both of which we'll hear more about in the talk later today. Before I hand over to Professor Collins, just a couple of housekeeping announcements. This is an interactive event. You can submit questions at any time during Professor Collins' talk or during the Q&A session afterwards in the Q&A box on the side of your screen. Please note this event is being recorded. So if you want to ask a question but would prefer for your name not to appear in the recording, it's possible to submit your question anonymously. Sounds like we've got lots of exciting questions already being submitted, but please keep submitting them during the talk. And if you see a question that someone else has asked that you would like to be asked, give it a thumbs up. We'll try and get to the most popular questions in the Q&A session. With that, I will stop talking and I will hand over to Gareth for his talk.
Thank you very much, Tom. I hope you can see my slides now. Welcome, everyone. It's a pleasure to be talking to you today about my research, some recent research. I'm going to talk about two things. I'm going to talk in the first part about some new things that we've learned about the asteroid impact that spelled doom for the dinosaurs. And then at the end, I'll tell you a little bit more about how we might be able to avoid a similar fate should another asteroid be unfortunately on collision course for Earth. Before I begin, I must extend a thanks to some other people that have been really influential in this work. So Tom, who is chairing this session, has been collaborating with me for a long time, but also we've been working with students that have contributed to this work: Narissa Patel, Sabina Raducan, and Oriel Ray, and of course my long-term collaborators, Joe Morgan and Sean Gulick. Okay, so Tom, can I just check that you can see my next slide now?
Yes, we see the slide.
Okay, great. And my laser pointing here. Okay, so before I start talking about asteroid impacts and their effects, I thought it would be important to start with saying a little bit about the evidence for why we think that it was an asteroid impact rather than anything else that was happening at the time that was the principal cause for the mass extinction. And whilst this story is very complicated, I think the most compelling evidence is one of timing. And this rather busy slide is from a marine record in the South Atlantic, showing you a period of time that straddles the boundary between the Cretaceous and the Paleogene when this mass extinction occurred, spanning about 1 million years across the boundary. And we can see very precisely where the asteroid impact is in this plot, because it was identified by a spike in the element iridium. Now, iridium is a rare, what we call a rare earth element, so it's almost non-existent in Earth's crust. But asteroids and other extraterrestrial materials are very rich in iridium. So whenever we see a spike, very large concentration in iridium on the surface of the Earth, it's very strong evidence that there was an extraterrestrial input of material. And in this case, That's asteroidal material that was scattered, debris that was scattered around the Earth and collected in this boundary layer at the Cretaceous-Paleogene boundary. And in this record, whether you look at the detailed evidence of extinction patterns from the abundant fauna and flora that were living in the oceans at this time, or if you look at geochemical proxies for the productivity, or if you like, the health of the oceans at that time, which is shown here, you see the same picture, which is a very abrupt collapse in the health of the ocean, productivity of the oceans, the diversity of species in the oceans at exactly the same time as the impact. And this suggests that it was a very acute, abrupt stress, like an asteroid impact, that was the cause of the extinction, rather than the prolonged effects of the large Deccan volcanism that was ongoing at the time, that started long before the boundary and continued long afterwards. So if the Chicxulub impact was caused by an asteroid, do all impacts of this size also cause mass extinctions? Well, the evidence is not really clear on this. It would suggest, and it would probably suggest otherwise. There are so-called 5 big extinction events in the last 500 million years, but the only one that has this really compelling evidence of a connection to an asteroid impact is the one at the end of the Cretaceous. So if some of these other large mass extinction events were not caused by an asteroid impact, why was that? Was it the case that we're missing some evidence of asteroid impacts in these previous events? Or, as I will hope to convince you today, was it the case that the Chicxulub impact was just unusually devastating? There was something unusual or unique about it which made it more catastrophic than typical impacts of this size. So let's talk now about the asteroid impact process itself. And what makes asteroid impacts so unique and so special is the amount of energy that's involved. And this comes from the fact that asteroids, when they hit Earth, are typically traveling at speeds of about 20 kilometers a second. Look, it's worth thinking about that number for a minute. 20 kilometers per second. 20 kilometers is about the same distance as a half marathon. So that's running a half marathon in a second. Well, for those of us that are more familiar with Couch to 5K at the moment, that's running a 5K race in a quarter of a second. At these speeds, when an asteroid, a lump of space rock, collides with an immovable object like the Earth, it creates a huge amount of force that squeezes the rocks on the surface of the Earth to perhaps about half of their volume. And this creates pressures and temperatures that are absolutely extreme. The only place we get pressures like this on Earth is right at the center of the Earth in the core. And the temperatures that are reached as the rock is squashed to these small volumes is thousands, tens of thousands of degrees Kelvin, hotter than the surface of the sun. So the only process that we're really familiar with that comes close to this is nuclear explosions. And so the dinosaurs, that if they were close enough to have seen the consequences of the impact, would probably have seen a fireball a bit like this one, which is a picture taken from a nuclear explosion in the 1950s. And what this is a fiery ball of gas and dust that's created when the explosion happens and heats the material up to these huge temperatures and transforms the rock into vapor, into melt particles, tiny particles that then expand rapidly outwards, forming this, as I say, this hot, fiery ball of gas that's often called a fireball. So if you were a dinosaur that happened to be within sort of sight of this huge fireball hanging, say, 100, 200 kilometers above the surface over Chicxulub, then you would have been toast. But actually, the effects of the heat emitted from this fireball would have been a relatively confined effect, a relatively regional effect. It would not have been sufficient to have the global consequences that must have happened to have caused a mass extinction. So what makes an asteroid impact become a global threat? Well, that is, we now think, to do with the fact that behind or within this plume of gas and dust that's expanding away from the crater is lots and lots of tiny particles that get dispersed all the way across the globe, that sort of shroud the whole of the Earth in a cloud of particles, and then take a long time to settle out through the atmosphere. This darkness that's then cast over the Earth, it's often called an impact winter, leads to inhibition of photosynthesis, global cooling of the climate, and it's these climatic effects that are of global significance, and we think were the major cause for the extinction event. Well, everything I've described so far really applies to any very large impact of this size. All of these large impacts will produce this fireball, this immense fireball, this powerful radiation, and scatter debris all the way across the globe. So why was the Chicxulub impact particularly hazardous in this regard? Well, one of the reasons is because of exactly where the impact hit. What this graph shows from a paper by Kaiho and Oshima is the distribution of organic matter in the sedimentary rocks on the surface of the Earth that could be liberated, that could be put into the atmosphere by a large Chicxulub scale impact. And what it shows is where the impact occurred, that's shown by this star, is in a place where there is a lot of organic matter, a lot of sulfur, a lot of carbon. And the problem with this, when you put it into the atmosphere, is that carbon dioxide is produced and sulfate aerosols, tiny particles, which are very effective at changing the climate. What the sulfur aerosols do is they are very effective at blocking out solar radiation, and so it's that and the distribution of sulfur aerosols across the globe that leads to this global cooling, and the carbon dioxide put into the atmosphere would then lead to a much longer period of warming. And what you can see from this map is that it's actually only about 1/7 of the Earth's surface that was covered in these sedimentary rocks rich in organic matter that would produce these climate changing gases and aerosols. So any other day of the week, chances would have it, and the Chicxulub impact would not have been as anywhere near as bad. So that's one of the reasons that the Chicxulub impact was bad. But what about other reasons? Was there something perhaps about the asteroid itself or the way that it hit that made the impact so catastrophic? Well, one of the things that we know influences the amount of dust and sulfur and carbon dioxide that would have been injected high into the atmosphere is the angle of impact. So this is the angle that the asteroid would hit the surface at relative to the surface. And what this plot on the left shows is basically a measure of how much stuff gets thrown up into the atmosphere versus the thickness of the sedimentary rocks along the x-axis. And for Chicxulub, we think that the sedimentary thickness there was probably about 40 to 60% of the size, the radius of the asteroid. So we're looking at this grey area in here. And what we can see there is that the impact that puts the most sedimentary rock material into the atmosphere is a sort of a moderately to steeply dipping angle of impact between about 45 and 60 degrees. It's the worst case scenario. It's worse than a head-on collision. It's worse than a very shallow angle impact. So is there a way that we can work out what the angle of impact was at Chicxulub to identify whether it was this worst case scenario or not? Well, to do that, we need to do a bit of detective work. We need to go back to the crime scene, and we need to see if there's anything about the structure of the crater that might reveal some hints of the direction or the angle of impact. Unfortunately, as this space shuttle image shows, if you go to the site of the Chicxulub crater now, there is not a lot to see. You can sort of just about make out this ring here, which is a ring of sinkholes, cenotes, in the limestone rocks underneath the Yucatan Peninsula that demarks roughly where we think the rim of the crater is. But the crater itself is actually buried underneath about a mile, almost a mile of sediments that have been deposited since the impact. And so we have to use other techniques, geophysical techniques, measurements that we make on the surface of the Earth that help us to image the subsurface and reveal the sort of the structure underneath both all of those sediments and underneath the crater itself. But interpreting these sort of geophysical observations is very difficult if we don't have a picture in our mind of what the Chicxulub crater looks like. And so to help, I've shown you what we think, or the crater that we think might be most similar to Chicxulub that we see on the moon. Chicxulub is what we call a peak ring crater, and the archetypal example of this is the Schrödinger crater on the moon. This is an absolutely stunning image of the crater. The crater is about 330 kilometers across, so it's about twice the size of the Chicxulub impact crater, but it has a lot of the same features. Okay, so we've got this very prominent rim with a fault zone stepping down into what is a very flat and shallow crater. So although the crater is, say, 300 kilometers across, it's only a couple of kilometers deep. It's extremely shallow and flat, and it's covered with a sort of a solidified pool of melt. But poking through that melt sheet is this ring of mountains in the middle. We call this the peak ring, and this is what gives craters of this type its name. So we think the Chicxulub crater is also a peak ring crater. We've been able to establish that from some geophysical observations. But it would also be helpful to understand a bit about how this peak ring forms, how peak ring craters form in general, to help us interpret some of the geophysical evidence. And what most of my research is about is using numerical simulations to try and reproduce this process. This is not a process that you can reproduce in the laboratory, because these craters are just so large and the velocities are so high. But using computer programs and run on a UK supercomputer, the Dirac supercomputer, we've been able to do simulations like this to try to illuminate what the cratering process is. And what you're seeing here is about a 15-kilometer diameter asteroid crashing into the surface of the Earth at about 15 kilometers a second. The first thing that happens is that we form a huge, very deep, bowl-shaped cavity in the surface of the Earth. What you're seeing here, these lines of balls are marking out layers or horizons in the target surface, and what you're seeing is the deformation of the entire crust, so which extends down to 30 kilometers below the surface. And what this shows you is that the cavity that's created to start with is about the same depth as the crust. So we're talking about making a hole in the Earth about 30 kilometers deep and about 100 kilometers wide. And a hole that big just isn't stable. So it collapses from the walls inwards, and the floor rebounds very spectacularly. And I want to draw your attention, as you watch this movie for the last time, to in the interior of the crater, beneath the surface of the crater, we see that the rocks beneath the surface have been pulled up towards the surface, or pushed up towards the surface. So deep rocks that were deep in the center of the crust, have been brought close to the surface. And that uplift extends all the way down to the base of the crust. So the deep mantle rocks beneath the crust have also been brought up beneath the center of the crater. And the peak ring itself is formed when this huge mountain in the middle of the crater, caused by the rebound and the collapse of the initial cavity, then collapses outwards, forming this sort of ring of peaks around the outside. So with that information, let's go back to this geophysical observations and see if we can make, see if we can understand what they're telling us about the subsurface structure of the Chicxulub crater. What we're looking at here is a gravity map. So if we measure gravity over the surface of the Earth, what it tells us is it tells us about changes in the density of the rocks that are beneath our feet. Where we see high gravity, it means we brought up dense rocks from deep closer to the surface. And where we see low gravity, it often means that we've broken the rock up, we've made it less dense, lighter than it was before. And although you can see lots of variations in gravity across this, the ones around the outside, so down here and down here, are not related to the impact. These are things that were pre-existing variations in density that existed before the impact happened. What I want to draw your attention to is the sort of bullseye pattern in the middle of this gravity, where we have this central high, gravity high. So this reflects this uplifted dense rocks from deep below the surface of the Earth that were brought up closer to the surface by the collapse of the crater. And that's surrounded by a gravity low, which is where the peak ring is, and this is where the rocks have been most fractured and their density has been reduced. And if we look at the location of that central uplift and that peak ring relative to the center of the crater, which I've highlighted, the outline of the crater I've highlighted in red here, what we see is that uplift is offset to the southwest. Okay. On the other hand, not shown on this gravity map, we can also plot where that mantle uplift was. So if you remember, that's the mantle is the dense layer of the Earth that's beneath the crust. And if we look at where that has been most uplifted, we see that that is to the northeast of the crater center. So we've got this alignment of these centers. The mantle uplift center seems to be to the northeast, the crater center is in the middle, and the peak ring center is to the southwest. So we observed this and started asking ourselves the questions: does this asymmetry, does it indicate the trajectory of the impact, and can it tell us about the angle of the impact? And so we did another set of numerical modeling, and I'm going to show you the results of those simulations now. So I'm going to show you a movie here where we've got again, about a 15-kilometer diameter asteroid. It's actually a 17-kilometer diameter asteroid striking at 12 kilometers a second at 60 degrees. The upper layer is the sediment, where the sedimentary material is. Then we have the gray illustrating the crust. We have the dark gray as the mantle. The red material is showing you the material that's going to be melted by the impact. So that's going to form this pool of melt in the center of the crater. And the blue shaded material is what's going to end up forming this ring of mountains, this peak ring. So if I play this movie, what you'll notice is that as I described before, we form this deep bowl-shaped hole in the crust that is about 30 kilometers deep. That collapses, bringing this mountain of rocks upwards, which then subsequently collapses outwards to form the peak ring, the final peak ring crater. And again, the crater is sort of covered in the middle with this melt pool. Okay, so let's step through that simulation in a little bit more detail to see what happens. And what I've done here is I've highlighted in the yellow circle the mantle, the bit of the crust mantle boundary that's going to end up the most uplifted during the impact. So we'll follow where that progresses as we go through the impact. In the first 20 seconds of the impact, it's pushed down as we form this deep bowl-shaped hole in the ground. And then after about half a minute, that crater starts to collapse upwards and pulls the mantle closer to the surface. And notice that as the uplift is moving, it's moving in the downrange direction. So it's going in the same direction that the impact trajectory was following. And then after 3 minutes, we formed this huge mountain in the middle of the crater. Notice from the scale here, we're talking about forming a mountain more than 10 kilometers high, right, which would dwarf Mount Everest. And we formed that in 3 minutes. This is a spectacularly fast and energetic process that involves moving volumes of rock that other processes really can't do. Okay, and then after this, we see that the central uplift collapses downwards and outwards, and that's what's going to form this ring of peaks in the middle of the crater. We've got the melt pool sitting in the middle of the crater, and if we plot where the middle of that, the center of that peak ring is, that's the blue circle, and you can see that that is offset to the downrange side of the crater. So the dashed line shows you where the center of the crater is, and what we see that in this 60-degree impact, the mantle uplift is offset uprange, and the peak ring crater is offset downrange. Okay, and this is exactly the observations that we saw earlier in the talk. So this suggests to us that the trajectory of the impact was following this arrow, so it was coming from the north-northeast and moving towards the south-southwest. And it also tells us that the angle of impact was probably about 60 to 45 degrees. When we run simulations at those angles, we get results that match the observations. If we use a steeper, so say a 90-degree impact or a 30-degree impact, we just don't see the same observations. So it does appear that in this case as well, the dinosaurs really had the worst of luck. So there's the summary of this part of the talk. The take-home message is that there is, I believe, mounting evidence that the Chicxulub impact was, if you like, a perfect storm. The crater asymmetries that we've looked at Chicxulub together with this modelling, suggests that the impact angle was steep at 45 to 60 degrees and from the northeast. And this is the most efficient angle for releasing these sulfate aerosols, these tiny particles that stay in the atmosphere for a long time, inhibiting photosynthesis and causing global cooling. And so it was the worst case scenario for the dinosaurs. So that was the perfect storm. But what about us? If we were faced with a similar scenario again, could we do any better? And how might we avoid a future impact? Well, there have been lots of different ideas proposed for how we might deflect an asteroid if one was spotted on collision course for Earth. And some of the more well-developed ideas are shown in this picture, and they include things like a gravity tractor, which is where you park a heavy spacecraft next to the asteroid and use the gravitational attraction between the tractor and the asteroid to slowly pull the asteroid off course, up to probably the only option for a huge asteroid the size of Chicxulub, which would be to detonate an explosion either on or to the side of the asteroid and deflect it in that way. But by far the most practical, sensible and method is to simply fly a spacecraft into the asteroid, and this is known as the kinetic impactor method. And this method is going to be tested very soon by NASA's DART mission. This movie is an illustration of what the DART mission will do. So it launches in 2021, and in 2022 the spacecraft will collide with the Dimorphos asteroid, which is part of the Didymos binary asteroid system. So Didymos and Dimorphos are a binary asteroid. So Dimorphos is orbiting around the Didymos asteroid. And the reason for choosing to conduct this experiment, this demonstration of our ability to deflect an asteroid on a binary system, is because this particular binary system is a so-called eclipsing binary. So what that means is that from Earth, we see the secondary, the moon, if you like, of Didymos going in front of Didymos, and therefore from Earth-based observations, we're able to very accurately measure its orbit. And so what we'll be able to do after impacting the spacecraft into Dimorphos and very subtly changing its orbit, from Earth-based observations, we'll be able to measure that very small change in its orbit and work out how effective that deflection will be. So why am I interested in this asteroid deflection mission? Well, because this will be a very rare opportunity to learn more about the impact process and actually learn about how efficient this deflection process might be. In a very simple way of viewing this deflection uses just a simple principle of the conservation of momentum. So if we imagine that we have our spacecraft with mass mi traveling at a velocity which in the case of DART is going to be about 6 or 7 kilometers a second, striking an asteroid, and we'll say that it's at rest, then the speed of the deflection we can work out under the assumption that the spacecraft and the asteroid then start to move together with a small velocity, and that is given approximately by the momentum, the mass times the velocity of the spacecraft that's impacted, divided by the mass of the asteroid. Okay, if that was the only story, then this wouldn't be a very difficult problem to analyze. But actually, what this analysis is missing is the fact that because the spacecraft is traveling so fast, it's going to produce a crater on the surface of the asteroid, and it's going to throw out a lot of high-speed debris, just like the Chicxulub impact, away from the crater, and that ejector is going to carry momentum with it, and that momentum provides an additional thrust to the asteroid. It makes this deflection more effective. So we've added this extra momentum to this equation, telling us how much the velocity changes. And this, and the interesting thing is that the amount of momentum in this ejector is actually something that can be many times larger than the momentum of the spacecraft itself. And so what we've been doing, and one of my students in particular, Sabina Raducan, has worked on in her PhD thesis, is to simulate the DART impact happening on a variety of different asteroid materials with different porosities, different strengths. And what she's found is that the deflection efficiency, so how much more thrust you get from this ejected momentum, depends very sensitively on what the asteroid is made of, how strong it is, how compact it is. You can see that this deflection efficiency, which would be 1 if the ejector had no enhancing effects, can be many times higher than that if the asteroid is particularly weak or if it's particularly compact. So what this means for the DART mission is that although the DART mission will definitely be able to demonstrate that we have the ability to deflect an asteroid and measure that deflection, to get the most scientific value from this experiment, we really need to know more information about the asteroid that we're hitting. We need to know its porosity, we need to know its strength. And for that reason, among many others, ESA is launching a partner mission to this called Hera, which a few years later will visit the Didymos and Dimorphos asteroids to fully characterize them, to measure, to make lots of measurements of both the crater formed by the DART impact itself and the properties of the asteroid, so that we can not only validate our ability to deflect an asteroid, but also learn and test our models of that, so we're better prepared to use this technique should we ever need to do so in the future. And with that, I'll stop there, and looking forward to answering any questions that you have.
That's great. Thank you, Gareth, for that. That fascinating talk. So we'll be moving on to the Q&A session shortly, but before we do, just a couple of reminders from me. So you can continue asking questions in the Q&A section on the side of your screen. We've had loads of great questions come in already, so really looking forward to discussing those with Gareth in a moment. Remember, we are recording this session, so if you would prefer for your name not to be in the recording, you can still ask your question anonymously. And remember just to keep liking the questions that you would like to see answered. We'll do our best to tackle the most popular questions as we go through the Q&A. So while I give Gareth a few more seconds to catch his breath after that talk, I'll just draw your attention to the next Science Breaks event, which is on Thursday, the 15th of October, when we'll be hearing from Professor Cristina Lo Celso, and she'll be discussing the battle against leukemia. So with that, I think we'll start the Q&A now. And so the first question I think we want to ask comes from Ronnie Zhang, and he asked, well, what's the likelihood of another asteroid clash on Earth?
Well, that's a good question, Ronnie, and I think I've got another slide here. Let me see if I can find. Yeah, here it is. So so this slide might help to answer this question. So it really depends, Ronnie, on whether you're interested specifically in another event as catastrophic as the KT or the KPG impact that did in for the dinosaurs, or whether you're interested in events that could be smaller that happen more frequently. So this plot is a very busy plot, but what it's showing to you is, as a measure of the size, if you like, of the asteroid in various different ways, what's the interval or the average interval between impacts of that size on Earth. And so for a KT impact, so something about the size of the one that did in the dinosaurs, that's about 10 kilometers or so across, we think the average recurrence interval is about 100 million years. But for something much smaller, so something maybe 50 meters across, which is similar to the event that happened over Russia in 1908, the Tunguska event, the frequency of those events is about 1 every 100, couple of 100 years. So those events, which wouldn't have global effects but can have very significant local effects, happen much more frequently.
Okay, that's great. I think that actually answers another question we had from Mark Nikitas, who asked, when is the most likely impact on Earth due to happen, and what's the probability? I think you sort of answered that by saying it's the smaller things there, but do we know when it's going to happen?
Well, yes. So this plot might imply that there's a sort of a regular schedule, like a bus timetable, of these things, but that's not the case. You can't read this like a bus tidal. It doesn't mean 100 million years impact interval does not mean we get one every 100 million years. What it means is that averaged over 1 billion years, we might expect, say, 10 of those events. But yes, the probability of something happening on a Chicxulub sort of scale is many times smaller than the probability of a much smaller, less damaging impact. And indeed, small things, small rocks are entering Earth's atmosphere all the time, and we see them as shooting stars, of course, in the sky.
I mean, that also kind of leads into the next question I was going to ask as well. So this came from Ava, and she asked, we think we've discovered 95% of extinction-sized near-Earth asteroids, but we still missed lots of the medium-sized city killers. What would be the impact of one of these hitting a populated area? And can we get any better at spotting them?
Yeah, that's another great question. Actually, this so the red curve on this plot, it's a little bit out of date. It goes back to 2009, but that shows you exactly Ava's point that telescopes have been looking for these large hazardous asteroids for a long time, and you'll see that in terms of the fraction of these asteroids that we think exist that we've spotted and are tracking, our coverage of the very large ones is very high. So that really reduces the risk of a large asteroid striking Earth in the next 50, 100 years to almost zero, because all of the ones that are in potentially hazardous orbits, we know where they are, we're tracking them, and we'll know, and we know that they're not coming anywhere near us for the next 50 years or so. But yes, as you go down in size, and so we're going down here in absolute magnitude, so this is the sort of the brightness, if you like, that the asteroid would appear in a telescope to an astronomer, we start to see that the red line lies quite a long way below the blue circles. And that's because these asteroids are much more difficult to see, they're much smaller, and so we have we've catalogued many fewer, in fact a very small proportion of things that are perhaps a couple of 100 meters or less in size. The good news is that those types of events are not global threatening events. More good news is that they also happen very infrequently. We're talking about every 100,000 years or so. But yes, if one was happening, they could be very devastating in a sort of in a local way. That this fireball that's produced, other hazards like earthquakes, tsunamis if the asteroid struck in the ocean, blast waves in the atmosphere and strong winds that behind that, all of those effects would happen if an asteroid of that size struck the Earth. Because those effects are relatively localized, then the key thing there is where that impact happens. If it happens in the middle of the ocean, middle of the Atlantic Ocean, or in the middle of the desert, the middle of Antarctica, it would have minimal consequences. But if it did happen close to a populated environment, then it could be very damaging indeed.
Great. So the next question then, I think we're kind of leading into this, and you talked a bit about this in your talk, Gareth. So from Nigel Patterson, he asked, well, what about stopping the next one? What kind of lead time will we need? When was Chelyabinsk first spotted by any near-Earth object observatories?
Yeah, so that's a good question. So I kind of glossed over this slide, if I go back to it here, but in the bottom right here, so this is a plot of, on the bottom right, about showing you when you might use different asteroid deflection techniques, depending on the size of the asteroid and the warning time. The longer warning time you've got, the better, because it means you need a much smaller, what we call delta V, so a much smaller impulse to the asteroid to change its course, because you've got that, you've got a long time for that small change in speed to turn into a large change in distance. And the technique that you would use would also depend on the size of the object, because obviously there's a limit to the size of the spacecraft that we can build and launch off the surface of the Earth, and so that limits our ability a little bit to deflect an asteroid using the kinetic impact method, unless we flew up many spacecraft to have a sort of a cumulative effect. In terms of the Chelyabinsk event, so what was really interesting about that event, we had almost no warning for the Chelyabinsk event because of the part of the sky that it came from. It came from the direction of the sun, which is not somewhere where astronomers can not part of the sky that astronomers can observe. But that same day, astronomers were pointing their telescopes in a different direction because a close approach had been predicted of a completely different asteroid on a completely different trajectory that was going to pass between the moon and Earth. And so, yeah, we were all geared up looking for in one direction for the asteroid, and from the other direction came the Chelyabinsk.
Okay, so we've got a few questions talking about you showed some computer simulations in your talk, Gareth, and there's a few questions talking about that. Well, first, Mark just said he loves the movie, which, that was nice to hear. And Caroline said she liked the computer simulation of the impact. How long would that have taken in real life? Would it be minutes, hours, or days? And another question similar to that from Lincoln Pang, he said, how long would it take for the asteroid to create its full effects?
Yeah, so these questions about timing are really they really make you stop and think, because it's quite astonishing how fast things are happening. So yes, I'm showing those simulations in a few, maybe in 30 seconds, but it's not actually that much longer that the real event happens. So for the Chicxulub event, I think I talked about the Chicxulub asteroid was, say, 10-15 kilometers across. It's traveling at 20 kilometers per second. What that means is that it travels its own distance in about a second. So the very beginning of the process, the formation of this fireball happens almost instantaneously in about a second. The growth of the crater is less than a minute, 30 seconds to form a hole in the crust that's 30 kilometers deep and 100 kilometers wide. And then that collapse process that brings up this central mountain of rocks, and which then collapses again, that probably happens on a scale of about 10 minutes. So slower than the simulation that I'm showing you, but still incredibly fast when you compare it to sort of traditional or standard geological processes. How long the effects would last is again, there are lots of different timescales. So it probably took about a day for the debris to sort of circle around the globe and sort of smother the Earth in darkness. How long that lasted depends on the length of time it takes for the particles to settle through the atmosphere, and that might have been months. But the cooling that then produces is probably something that went on for years, perhaps decades, and then there are other longer term climatic effects that probably went on for even longer than that.
So, I mean, we're talking then about the long-term survival as well of the dinosaurs. So there's a couple of questions. Mikhail has asked, did any dinosaurs stand a chance of surviving at all? And Lewis has said, what characteristics, if there were any surviving ones, what characteristics do those surviving dinosaurs have not to perish after the impact?
Yep. So that's a really good question, and there does seem to be something there in the fact that everything that seemed to have a mass of about 25 kilograms, I think it was, or something. So anything bigger than that was history. And there could be lots of different reasons for that. So big dinosaurs, big animals. They need a lot of food. They need a lot of area to source that food from, and so they're more vulnerable to changes in habitat. So it could simply be a matter of that, but also certainly for anything that was close enough that it would have been affected by the fireball, it would have sort of received this thermal radiation. If you're a big dinosaur sort of wandering the plains of North America, there's absolutely no way to hide from that kind of thermal blast. But if you're a small creature that could sort of burrow underground, perhaps, or go into the riverbank, find a little cave, then you could probably have escaped that sort of tens of minutes, hours or so of extreme sort of thermal radiation.
So then, following on from that, what about humans, right? If we had been around at the time of the impact with our current levels of technology, Maxi asks, would we have had any chance of survival then?
Yeah, so I'm optimistic. So one of the things about this idea that this was the perfect storm is a good news story, in that if this event did happen again, well, hopefully it wouldn't be 60 degrees, and hopefully it wouldn't be in the Yucatan Peninsula on top of it, into these very sort of carbon-rich, sulfur-rich rocks. And so, and maybe if that was the case, then maybe the global climate effects wouldn't be quite as severe, and that we would have been able to, life would have been able to survive through that. But even if it was, what's actually very remarkable as well, which I haven't really touched on, is how quickly life recovered afterwards. So even in the center of the crater, where you might expect that the effects would have been by far the worst, and that life would have taken forever to sort of to come back, the recent drilling that was done has recovered a record of the sort of recovery of life inside the crater. And what that's shown us is that it probably was only years before some organisms were able to recolonize the crater, and not long after that, maybe hundreds of years before, life was flourishing again. So again, this talks to this idea of the impact being an acute stress, a very short-term stress. But what that also says is that maybe if we could sort of shelter ourselves somehow for a relatively short period, like maybe months, years, without needing to rely on agriculture or things like that, maybe there's a chance that we could make it through that initial impact winter.
What about trying to deflect it? Do you think are our current levels of technology at the point that we could have stopped it altogether?
For the 15 kilometer a second asteroid, probably not. I mean, so again, yeah. So this graph here, I don't know whether you're still seeing it, but so with a spacecraft that we can build and launch right now, and let's say we had 10 years warning time, deflecting a 100-200 meter diameter asteroid is something we can do. So a city killer we could avoid. But something that was 10 kilometers across, that's 100 times bigger in diameter, so that's 1 million times bigger in that. We'd need to send 1 million spacecraft to intercept the asteroid, and that's just not achievable. So I think probably not right now. Is the honest answer to that. But we're okay. We know where they all are at the moment.
So I think we're getting close to the end of our time. There's a couple of questions I did want to ask you from here. So Caroline asked, well, what would happen? Would there be any difference if a large asteroid hit in the deep ocean instead of the land? Would the impact be so energetic that it doesn't matter? You've covered some of that with sort of talking about the different rocks you've got to hit. But if we had one in the deep ocean, would that be any different?
It depends on the size. So if it was this 15 kilometer diameter asteroid like a Chicxulub, then there's very few places on Earth where the ocean is deep enough that would have a huge effect. Obviously, you would create a lot more water vapor in an impact into a deep ocean, and you would generate very large tsunami waves, which could have a very sort of devastating effect. But if the asteroid was very large, it would still it would still form a crater beneath the surface, and it would still potentially release a lot of dust and vaporized rock into the atmosphere. If it was much smaller, if it was say 200 meters across, then you wouldn't get a crater on the sea floor. You would just form a crater in the ocean, and so the main hazard from that would be the tsunami waves that were generated.
Okay, so I think let's just squeeze in one really quick one before we finish up. So there was an anonymous question. It said, what happened to the Chicxulub asteroid itself after the impact? Did the asteroid just shatter, or has it been lodged or buried inside the crust of the Earth? Or what happened to the asteroid?
So as I said, as I talked about at the beginning, where these extreme pressures, this extreme compression that happens to the rocks on the surface of the Earth also happens to the asteroid. So the asteroid is undergoing the same fate. So it's turned from a very cold ball of rock into dust and vapor, and so it's part of this ball of fire, this ball of hot gas and dust that then expands out and scatters the debris all over the Earth. And that's why this boundary layer, this material that came back to Earth and settled down, why it has this iridium anomaly in it, the signature of the asteroid material that's been redistributed across the globe.
Okay, that's great. So I think we have to start wrapping up now. So I just want to say thank you very much to Professor Collins for the fascinating talk and answering all those questions today. Thank you all for all your questions that you submitted. I apologise we couldn't get to all of them. I've got over 50 questions showing up at the moment, so I do apologise we couldn't answer them all. But I hope you had a good time and learned something from Professor Collins today. So yeah, just thank you again for joining us for this Science Breaks event. Please join us again for the next Science Breaks, which will take place on Thursday, the 15th of October, when Professor Cristina Lo Celso will discuss the battle against leukemia. So thank you again.